So I will go through this presentation, and you have already gone through the theoretical part. So mostly here I'll go through some of the simulation results and some of the laboratory work we do. So here we'll be going through the workflow for quantifying this gas condensate blockage effect. So if we have a project, then what are the different steps just we have to follow?
You have to just click on the screen. Just click on the screen once, and then it starts to work.
No, just click on the screen.
Screen?
Yeah,
Okay, here.
There? Now you can go there. There it is, right?
Yeah. So I'll present this one in three different phases, the work we do. First is the evaluation of the condensate blockage well performance. And mostly we'll be going through the simulation results here. And the next step will be measurement of the relative permeability in the laboratory. So how to design the lab experiments and what to consider while doing the design, and then what the interpretation of the results. And then we have to develop the relative permeability model, which should include both capillary number and Darcy effect. So once we have the capillary number model from the lab experiment data, including velocity effects, then how to implement those results in a reservoir simulation model. Here we will be going through Eclipse 100 and 300.
So this initial step.
Yeah.
The company might have a full field model normally when they come to us.
Yeah, so normally we ask for a full field model, because from full field model we need like reservoir fluid compositions, equation of a state model, and also this reservoir permeability, porosity, heterogeneity. How is that?
Layering.
So, layering, yeah. So either we need the full field model, or if there is available, then we can have a single well model also.
Single well model or full field model?
Yeah.
Okay.
So once if there is full field model, then we create a single well model based on honoring the full field model parameters and all the properties were signature.
Okay.
But if you have a full field model, like for example, hundreds of wells, how do you choose one well?
Okay, so generally what we do, first we try to run the full field model and try to take the performance of all the wells. And then generally we select one good performance well, one bad performance well, and one average well.
So three different kind of category wells. Really good well, average well, and a poor well.
Yeah. So this is showing what is the gas condensate blockage. And this figure, I think we have gone so many times during this course. The same thing here is showing three different regions, region 1, 2, and region 3. So what we do if we are going to evaluate the condensate blockage, so first we have to make this single well model. And this single is the first with the fine graded model. It can have the number of layers same as in the full field model. So this single well model can be provided by the client, by the company, or we can set up ourselves based on provided full field model. And this single well model should have all the layerings as in the full field model. So first we make this fine graded model, generally fine graded radial model. And then also we make equivalent coarse grid Cartesian model. And this coarse grid Cartesian model should have a similar gridding as in the full fill model. Similar, I mean del X and del Y grid size thickness. And then we compare the performance of the single wheel model and fine grid and radial model. Fine grid and coarse grid model.
But if you have a full fill model, can't you just, like, for example, you have selected one well, can't you just take the section of that well and just inactivate all other cells? You don't do that.
Yeah, but we need to make one fine grid radial model also equivalent. So it's not only that we are getting this coarse grid model from the full fill model. So we have to make equivalent radial, and then in that way. So if you have in the coarse grid model, your permeability will be varying. Like if you select one well and if you have 10 grid cells in X direction, 10 grid in Y direction. So, but this permeability will vary. Even in the layer number 1, grid to grid permeability will vary. And if you take that particular well from the full fill model, and if you want to make a radial model, then it will be difficult. We don't like how to just vary the permeability as we go away from the well. So what we try to do, we take this a particular I and J, and then whatever is the permeability, X permeability in that particular I and J, we try to have in all, in the horizontally, we try to keep the same.
So uniform permeability in each layer.
Yeah, uniform permeability in each layer. So layer 1 will have, let us say, 10 millidarcy, but it will be 10 millidarcy throughout. Layer 2 may have 5 millidarcy, but it will have the 5 millidarcy throughout the layer. So that's why. So that becomes the that's the reason why we have to make the single well model, because we want to make this fine grid radial model also.
And here, like, do you also sometimes see that the companies provide you like this geological model, or do they always provide you full fill simulation model?
We get a full fill simulation model, but sometimes like we can get this geological model also.
Okay, with very fine layers.
Very fine. In that case, we have to just do some upscaling.
Okay.
And there are different ways of doing the upscaling. Like generally, we had recently one study. In that particular paper, there are more than 1,000 layers. I think 2,000 layers.
Okay.
And then we had to just come with this 100 layers.
Okay.
So in that case, we have to do this upscaling. Any question before we go further? Okay, so this is showing one setup. This is the coarse grid model, the base case we have taken. So in this particular case, we have taken 11 grid cells in X direction, 11 in Y direction. And it's a single, only one grid cell in Z direction. And thickness is dxdy 150 meters. And this was taken, this is a simple model we have taken, and this was taken from SP paper of 117930. And then if we do the same base case, so this is the performance based on this coarse grid model we have. So the model was simulated with the maximum gas production rate of how much? 500, 500,000 standard meter cube, and then I think the bottom hole pressure constant was 1,000 bar. 100 bar. So we have in this particular case, if we simulate, then we are getting a plateau period of 8 years. And then this is showing the same coarse grid and equivalent fine grid radial model. In the fine grid cells, we have 10 grid cells in radial direction and one grid cell in Y and one in Z direction. And the inner grid cell is very small, 0.05 meter. That's the DR of the first grid cell. So it's a very fine grid near the wellbore. So if in feet, it becomes 0.15 feet. Yeah.
Sorry, so does that mean that you switch from coarse grid model to fine grid model to evaluate the effect of condensate? Is that what you're saying?
Yeah, so what we are saying that if we simulate the reservoir using fine grid model, we'll expect the true result. In this case, we'll have this effect of condensate blockage. We are covering the effect of condensate blockage in fine grid model.
Okay.
But in the coarse grid model, if it is simulated as it is, then we will not be able to cover the effect of condensate blockage. And you'll see the difference.
I mean, here you would have then the effect of geometry, which is now radial, plus the refinement.
Yeah, exactly.
Yes.
And you could have hundreds of layers if you wanted to have the vertical heterogeneity, and of course that brings complexity, but it's real complexity.
Can you have a combination of both radial and Cartesian geometry in Eclipse? Like around the valley, you have radial, and then you can.
Yeah, you can do this local grid refinement
with the radial.
Yeah, so you can define what type of local grid refinement you want to have.
Okay.
So, but if you are doing this local grid refinement in the fulfill model, so if you have 100 wells, you have to do this local grid refinement for the 100 wells.
Okay.
There's a question about if you have the same gas in place in both models.
Yeah, so in this both model, both are identical in the sense that the thickness is same in both the models. Total area will be same. Total volume will be same. Total in place will be same. Permeability will be same. So only the surface geometry is different. In one we have the radial, and other we have this.
So how would you differentiate then between the effect of geometry and the effect which is coming from the refinement? I mean, wouldn't it be the other way that you just refine the coarse model to approximate the radial flow? Because now you have like superposition of geometry and refinement. You compare it with a different model which is coarser and has a different geometry.
No, I don't expect the difference. Here we are in the radial model, we are capturing due to refinement, we are capturing the condensate blockage. But if we have the same drainage area, if we don't, what is that?
Yeah, I mean, your single well model should be the best numerical approximation to the correct answer. You're trying to create a model that gives the most correct answer. And then when you go to the Cartesian, of course, you can get a different answer just because it's Cartesian. Or it can be because it's Cartesian and it has coarse grids, et cetera, et cetera, et cetera. So, but, you know, if you had any question about the Cartesian coordinate system giving you an incorrect answer, just run with single phase gas, right? For example, if you get very similar results with single phase gas, then the grid discretization and geometry doesn't really have an effect on basic single phase flow. So that's what would happen here if you basically.
Yeah, so we will not see the effect of geometry.
Yeah.
It's only effect coming due to this fine grid gradient. So if we simulate the same system with fine grid radial model with grid refinement near the wellbore, so we see this black line.
What kind of flue system is it? Like green gas, rich gas?
It's a rich gas.
Okay. We will see.
We will see.
Yeah.
We'll go through the effect of the richness also. So in this particular, in this simulation case, what we are seeing this in the fine grid model, our plateau period is nearly half.
Mm-hmm.
And the difference between a red line and a black line is showing the effect of condensate blockage.
Mm.
So for this geometry, for this system, for this relative permeability, for this fluid's richness, we see large impact of condensate blockage. So, and why it is happening? Here, it's this is the reservoir pressure, the blue line, the same case. We are just trying to see what is happening. So here, blue line is the reservoir pressure, and from the simulation model, and this red line is the bottom hole flowing pressure in the coarse grid model, and the black line is bottom hole flowing pressure in the fine grid model. We see the bottom hole flowing pressure reaching 100 bar at the around 3.5 years when plateau ends, and here bottom hole flowing pressure, if you see, it's hitting 100 bar at around 8 years.
The reservoir pressure, is it for fine grid or coarse grid?
Reservoir pressure, if we, it has been taken from fine grid.
Okay. But that should be different for the two cases, right?
Yeah, it will be different after some time, because here before the plateau period, yeah, it will be same. So till 3.5 years, since the cumulative production is same in both the cases, so we see the reservoir pressure will be same. So just to see what why we are getting the difference in fine grid and coarse grid, let us say we take at the end of 2 years. So at the end of 2 years, our reservoir pressure is 400 bar. And we have seen this one, total mobility with pressure. So this is the black, this mouse movement will be seen, or
I think so.
Yeah.
You can also add a pointer if you want. If you want, if you want to be fancy.
Okay. Yeah. Yeah. So this is total mobility with pressure. So it's the same curve in upper right and lower right. So what is happening in the fine grid model? Here it goes from like in this particular case, the reservoir pressure is 400 and bottom hole pressure is 200. So what is happening? We have this constant C and then area. C is same in both the cases. So in the fine grid model, it will follow this total mobility curve, and it will try to find the area because we know the rate. For example, at the end of 2 years, our production rate was 500,000 meter cube per day. So we know the rate, we know the C, so we have to find area. So in the fine grid model, it will follow this line and it will get the area which will satisfy this rate. And then this area, it is getting when we have this bottom hole pressure of 200 bar. But in the coarse grid model in Eclipse simulation, it will find the value of mu g, bg, whatever at the grid cell pressure, and then it will just take the same and then it will find the different bottom hole flowing pressure. So that's why in this particular case, the area is same in both the cases, but the way it is taken into is different. So in this coarse grid model, we are getting 300 bar at the end of 2 years.
The C value, it will be different, right? For the two cases, because in the fine grade, the well geometry, like you have changed the grid system,
and the connection factor will be the same.
Okay.
Well, this is really the C of the entire well. The well index probably will be different, but this on the right is C for the entire well. It's replacing the whole model. You know, the steady state rate equation is C of the whole well log RW. Okay, and the area should basically be the same. Or it's just that the areas, the integral of the areas of mobility in the coarse grid model, you have a higher mobility everywhere, so you need less pressure drop to get the same area.
Yeah.
You know, you got two phase probably in all the grid cells, but the KRG reduction is very low because the oil saturation is not very high. You don't have any region 1, so to speak.
Other way is just to simulate that don't go in a two phase. You can do one simulation where you are only above the dew point, bottom of flowing pressure above the dew point. Then we get the value of C. Okay, so what we have see why the region we are seeing the way it is calculated in the fine grid and coarse grid. So, and then some other sensitivity case we can just try to see. So what is the impact of the condensate blockage if we have a different type of rocks or a permeability? So in this case, this is the simulation case where we have changed the permeability from 5 millidarcy to 1 millidarcy. And now we see of course, we have 1 millidarcy, so performance will be different. And if we have, but the difference between fine grid and coarse grid model, we see a large impact. So basically what we are trying to say that if we have impact of condensate blockage is higher in case of lower permeability. So like yesterday we saw that if you have KH of more than 10,000 millidarcy feet, you have no effect of the condensate blockage, and if you have less than 1,000 millidarcy feet, we have. So similarly, it's saying that for the low permeability reservoir, we have more effect of the condensate blockage. You can see also the case for in the base case, we had 5 millidarcy. So, what is the difference between here? Here you have 1 millidarcy. Okay, this is maybe a 0.1 millidarcy. Even so, maybe heading is so here we see even a larger impact, and this is a 0.1 millidarcy, I think.
But generally, when you get a project and you get a full field model, do you do the permeability sensitivity?
No, we don't do. But here, if we are showing that what we can expect if you have very high, let us 1 millidarcy high permeability, then you will not expect. So here just
this could be another well. This could be the poor well of the 3 that we picked from the model.
Yeah. That's right. This one, if we have the higher permeability, let us say in this case we are showing for 15 millidarcy. So here the difference between coarse grade and fine grade is small. So here we see that the impact of the condensate blockage, we have little impact. So here the main thing is that we are showing that if you have low permeability, you have a higher impact of the condensate blockage. Okay, here also we are showing that in this particular case, 15 millidarcy, we are producing at the rate of 500,000 meter cube per day. If we produce at higher rate, in this particular case, for the same 15 millidarcy reservoir, we are producing at 3 times higher rate, 1.5 million meter cube. So now here we see that the plateau period, it was it's only, let us around 1.5 years, and here in this case 3 years. Double. So the plateau period is double. So it's not only the permeability, it's also the production rate. So if we are producing at higher rate, then we can expect more effect of the condensate blockage.
Is this only the condensate effect? Because if you increase the rate, you also increase the contribution. I'm not sure what is more about non-Darcy effect, because then it's also increasing exponentially as velocity.
No,
should be a superposition of both.
We have not included impact of non-Darcy effect in this one.
No, there's no
non-Darcy scheme.
only the rel perm. No, there's nothing else added here yet.
Yeah, so still we have not included effect of non-Darcy flow in this model.
And there is no effect of capillary number.
No. So only here we are seeing the effect of the condensate blockage.
But why would you have more difference if you produce at high rates?
It's the pressure drop will be higher, like if you see this, if we go here.
Yeah, you get more higher pressure drop.
Yeah, so here if you see, so here. Can we explain other way also?
Well, yeah, I mean, you also have the degree of how much below. If you go to extreme, a really low rate, then you'll be the area between the reservoir pressure and the bottom of flowing pressure, as it gets smaller and smaller, has less effect. Okay, here you're drawing down. You don't need to go to the flowing bottom hole pressure. You're reaching it at 3 years here versus a year and a half. When you reach that at a later state, then the amount of pressure drop you need to get that rate when you have a much lower rate is less. So.
Okay.
Okay, so in this particular slide is showing the effect of grid cell size. So in the base case, in the red line, we had grid cell size of 150 meter by 150 meter. Now we increase the number of grid cells, decrease the number of grid cells, but increase the cell size. So keeping the total reservoir dimensions same, but increasing the grid cell size. So if we increase the grid cell size, even our performance, we are getting more plateau period. So it has impact till now we are not including any pseudo pressure or any special treatment. Just we are doing this simple default simulation. So here in the base case, the richness is 90 stock tank barrels per million standard cubic feet. So, and if we have this linear system like 60 stock tank barrel per million, then in the here also we see the impact, but if we see in relative, it was going from 8 to 4, but here it's going from 9 to 5. So here also we see, but it will be slightly lower impact.
So when you have a 90 versus 60, the dew point is the same, the dew point pressure.
Dew point will be different.
Different. Okay.
Yeah, because we are only changing the dew point will be different if you have 90 and 60.
Okay.
Reservoir pressure will be same, everything same, but due to change in the fluid composition, and the dew point will differ. In this simulation case, what trying to show, this is the relative permeability, and in this particular case, KRG is about 0.1 at the crossing, and this is the simulation performance in a fine grid radial model. What will happen? We change the relative permeability. So now let us say we have relative permeability, which is given by this red line. So this is gas saturation. This is the gas relative permeability for relative permeability set 2. And the black line is the base case. So in the red, we see...
The crossing point dropped down to 0.04, it looks like.
Yeah, so here in the red line case, we have a lower KRG at the crossing point. And here I just expected we are getting production rate is low compared to the base case. So we see the difference in performance due to impact of relative permeability.
I mean, this is an example coming back to the question from the last section. You know, it's very clear that you need to find out what are your relative permeabilities here. Because the performance is radically different for these two rel perm curves. The one is quite pessimistic, the other is more optimistic. They're both realistic, and not knowing which is which, the performance is so different. You need to find out.
Yeah, and in the lab experiment, we have already seen that this crossing we have seen from 0.03 in even very low permeability. Yeah, 0.025 also we have seen this crossing going up to 0.1. We can take this particular case in this relative permeability. So in this particular case, if we see with respect to saturation, like gas saturation of if we take at 0.5, our gas permeability is higher in the compared to the base case. And similarly, at any saturation, red line or this new relative permeability is better than the base case. So if we see, if we expect, then we'll expect better performance if we use this relative permeability set. But we are getting the same performance with the black line relative permeability and red line relative permeability.
The cross point is the same.
Yes. So in this particular case, the crossing point is the same, and we'll show in the later also the other plot also. But here, if you see in the terms of saturation, it seems that okay, our red line should get give better performance, but we are not getting.
Yeah.
So something else we
because
need to
here the red line has a critical gas saturation of about 0.1, and then in the other one it's about 0.2 something. So you mean that the critical gas saturation doesn't impact it doesn't have any impact on the performance.
Yeah, maybe critical or maybe some other property.
But the KRG versus KGKO or it should be very similar for these.
Yeah, so we are just we don't show. So we have to see, just to see why we are getting the difference in performance. We have to see this KRG with KRG CAN.
But you can see that they're identical at the crossing point, so they're not going to be separating very much otherwise. So it's.
So here we see there is impact of the relative permeability on the well performance. And in this particular case, we see large impact of the condensate blockage also. So what we do once we have to measure the relative permeability, so we have to do this laboratory measurement to get the appropriate relative permeability. And then we have to develop model which will include also the capillary number and non-Darcy effect. Of course, here I have not shown any simulation with capillary number and non-Darcy. That will come later on. So relative permeability has impact, and if it has impact on the condensate blockage, then we have to make the measurement in the laboratory. And in the next phase or next section, I'll go through how to do this design of the lab experiment, how to do the interpretation, and how to develop the relative permeability model. That is, you would like to include something before we go to the next phase or next section?
Yeah, I mean, basically the first evaluation was that you saw clearly from a realistic conservative and a realistic pessimistic rel perm that you had a big effect on the well performance. That means that the rel perm uncertainty has to be reduced from the not the previous slide, but the one before that.
Yeah.
So no, from the this one here.
Yeah.
That tells the whole story.
Yeah.
And you need to do that for a poor well, an average well, and a good well. Now, maybe for the good wells, you don't see any effect, but for the medium and the poor wells, you do see it. So then, you're not only going to have good wells. So this basically, this figure here is saying that you have to reduce the uncertainty in the relative permeability curves. The other curve, which showed no effect, was because the KRG, you basically are using the same rel perm in terms of blockage is identical for these two, because you can see that from the crossing point. So,
and you also showed that the gas rate, the flowing gas rate, has an impact. So when you do this work, when you do the work, how do you choose the gas rate?
You have the range of gas rates that you potentially will have to,
Or you just put it at the minimum bottom of flowing pressure from the beginning, or you choose a rate that gives you a plateau, certain plateau.
I mean, you give it a control, you give it a target, right?
Okay.
but with the minimum bottom flowing pressure being realistic for the surface control. But I think seeing that, you don't know exactly the individual well plateau rate because it's the sum of all the wells,
that gives you the field
that gives you the field rate. But you'll have a range. You can have between 30 and 50 wells in a field development, and you know that the contract is for half BCF per day, and then you have the range of the rates, and you have to run with that range of rates on the individual well basis. So when we get the full field model, they'll give us. You'll see that from the full field model what kind of range they're looking at getting.
Okay.
And the well rates.
Yeah. So what relative permeability is important for the condensate blockage? And I think we have seen this KRG as a function of KRG KRO. That is the most important. And this detects the condensate blockage in region 1. And region 1 is the main region where we get this effect. And as we have seen, this KRG KRO depends only on the PVT properties and the flowing composition of the fluid. And KRG as a function of KRG KRO is a rough property. Here it's a typo, just a typo. Yeah. Yeah. So what we have to do, we have to correctly model this model the effect of condensate blockage near wellbore. We have to measure basically KRG as a function of KRG KRO. So here they're showing the same thing when we saw the difference. So in this particular case, the same case we are showing, but here we are just trying to have this plot KRG as KRG KRO. So in this particular case, in this relative permeability, we saw this performance, and the main reason was we have this different KRG KRO relationship. In this particular case, even if we have with respect to saturation, we had different curve. Like for the red, we have a higher KRG at a given saturation, but we saw the same performance. The reason was that we had similar this KRG as a function of KRG KRO. So it was nothing to do with this critical saturation. It's mostly its impact, with this relationship.
So in the previous, to go to the previous, the small impact that you see in the profile, that's coming from region 2, right? Because of the different critical gas saturation or the critical oil saturation. You have different performance in region 2 for the two cases.
Okay, so for a...
Yeah, you have region 2 saturations may look different, but usually it has no effect on the profile.
Yeah, he's talking about this small difference.
Yeah.
Correct.
That's from region 2.
Yeah, that's right.
Go.
Then we have also, like we are showing some result in the lab. We have to also capture this, do the experiment where we have this high capillary number. And here what we are saying that, okay, there is impact of the capillary number on the relative permeability. We have seen the lab and the field performance also. And as shown previously, this capillary number is given by this pore velocity, viscosity, and then IFT. So here we have done some simulation including the capillary number effect. So this is the black line is the fine grade model without capillary number effect. And what we have done in the blue line, just we have included effect of capillary number. So I'll go through later on. There are two capillary number models in Eclipse, and here we are using this Whitson model and default parameters. So there are two parameters in the capillary number model as discussed earlier. It is the alpha 0, which is 10,000, and n was 0.065, which is default in Eclipse. So here, just in the only the turning on this capillary number effect, taking all the two default parameters in Eclipse 300. So here in this particular case, we see large impact of capillary number on the simulated performance. So in this particular case, we are taking this alpha and n default parameter, default value in Eclipse 300. But if we change the alpha, so default was 10,000, which is the blue. And if we have only 100, where this is the pink line, is if we take a small value of alpha 100, then this one is for 1,000, 2,000, 5,000. So here what we are trying to simulate was so that this alpha or capillary number model parameters have impact. So if we want to simulate properly, model properly, then we need to get this alpha from the live measure data. Because this, depending on the alpha parameters, the plateau period can vary from 3.5 years to 6.5 years. So which alpha value to take? And that answer we can get from the live measure data.
And this alpha, this is mainly a function of the rock quality, or both rock and fluid?
It's the rock.
Rock quality. And usually, if you don't have any measurement, the default value is good, and you can start with that.
And it was if you go and see in Eclipse 300, the default value is 10,000. And in the last 20 years, we have seen the alpha is somewhere between 1,000 to 5,000.
Okay.
And the reason is that this 10,000, which it was obtained in the initial publication, so those cores there for high permeability. I think 100 millidarcy and otherwise also even higher. So now the experiments have been conducted on the low permeability cores also, and then we see this alpha 0 lower value. So I think the default value is 10,000 is optimistic. So based on the experience in the last 20 years, if we have to recommend what should be the value of alpha, it should be somewhere, let us say 2,000 around here. Okay, so going through this non-Darcy flow effects, as we have seen previously also, that it reduces the well productivity. And this is one simulation case. Here we just took the black one is the base case without without capillary and beta, and this blue one is with the capillary number effect, and this pink is including the effect of beta. And of course, if you are including the beta, then what value of the beta should be taken? That also we have to either find from the correlation or we have to find from the live measurement. But for the correlation, there are so many different correlations for finding this beta based on the rock permeability, and the value will differ from one correlation to other correlation. So what we try to do, we also try to measure the value of beta in the laboratory, just to limit the uncertainty. But of course, we see here the impact of the beta for particular this case, or at this production rate, we don't see much impact.
Beta that's the second parameter for Shammer.
Yeah.
And
Right.
that can be determined from well test.
Core flow test is normally the way.
No, if I'm saying if you have a multi-rate test, if you do multi-rate well testing, different rates, you can determine beta.
You can get a composite well beta. But that has been reported by people like Ramey and Petrovich that they can be an order of magnitude different than what you see in the rock tests.
Okay.
And there's different theories about why that may be the case, but the well test beta is often quite different than the
Lab test.
than the lab test historically.
So what we have to do, so we have to develop a relative permeability based on the live measure data, which should include both the rock curve and then capillary number effect and turbulence effect. And that we develop or do based on the laboratory measurements. So the process before going for the laboratory measurements, we have to use a fluid. So what fluid to use? Either we can use the reservoir fluid to do the live experiment or synthetic fluid. But there are some limitations doing the experiment with the reservoir fluid, or we can say that it has been shown that this relative permeability based on the synthetic fluid, reservoir fluid, and if you design a synthetic fluid which can represent the reservoir fluid, so if you do the live experiment, relative permeability live experiments using the real reservoir fluid and synthetic fluid which represents the reservoir fluid, we get the similar result. I think it was published in the
Yeah, I think this
paper,
presentation I showed
before.
before.
So generally what it's done, generally experiment in the lab is done with a synthetic fluid.
But
First,
that synthetic fluid that you create in the lab, that's a good representation of the reservoir fluid.
Yeah, so that should represent the reservoir fluid. So reservoir PVT properties of the real fluid and the synthetic fluid should be similar. And also sometimes the reservoir fluid may contain H2S or CO2, which lab people, they may not want to do experiment. That real reservoir fluid. There also you don't have the reservoir fluid to do the experiment because large amount of PVT fluid is used here for doing the experiments.
Okay.
So there are so many good reasons doing this live experiment with synthetic gas. Generally, what we have seen that 3 to 4 synthetic components, they are enough to represent this real reservoir fluid properties, which are important for this relative permeability.
But when we say that similar PVT properties, so what are we talking about here? Like dew point pressure, that's one thing, and any other?
Yeah, we will see. I will show one match. So what the PVT properties are going in our relative permeability calculation. If we see this, for example, KRG by KRO, we are getting this VRO, 1 by VRO minus 1, and viscosity of the oil and gas.
And the composition with depletion.
But that transport, if you think it in terms of this PVT property, so the composition will transfer into the VRO and viscosity and oil and gas.
Okay.
Here, of course, we are saying synthetic fluids, we have dew point pressure close to the reservoir fluid. And how we design this synthetic fluid and whether we can design or not, that's given in this SP paper. Okay. So this is showing a case where all these symbols are from, this is a CVD experiment, and symbols are based on the reservoir fluid. So CVD, then liquid viscosity, the gas viscosity, and this IFT, which comes in the calculation of capillary number. So we try to match these four PVT properties. So for this particular reservoir fluid, to match this PVT properties, these four components, and this is the composition. If you take, then we see this, we get this black line. So this four component synthetic fluid is able to represent this reservoir fluid, the parameters we are interested in.
Okay. But when you are in the designing phase, you don't have the lab data. So you just use the default US?
Yeah, so we are using the US, and this is the pure components. If you see the C1, C5, and C10, so we take this default US parameters, default component parameters. And of course, just to make sure that whatever we are designing, we are getting similar. So we do this PVT live experiments on the synthetic fluid also. And if we need to change slightly parameters to match the PVT experiment on the synthetic fluid, we do later on.
And that will be mainly binary interaction.
Yeah, mostly it will be the binary interaction parameters.
The reservoir PVT description that you're comparing against can be either laboratory data and or a tuned equation of state for the reservoir fluid.
Yeah.
Often when we're given the model, we're given the tuned equation of state for the reservoir fluid. We use that to create these
Data sets.
These for comparison. Yeah.
And in the last 20 years, we have been able to design this synthetic fluid for almost all the projects, either 3 components or 4 components. And what we have found is diphenyl methane that has been a very good component in designing other synthetic fluid. So we use a lot this one, diphenyl methane. In this particular SP paper, I think there are around 10 different types of reservoir fluid we have taken, and we have designed synthetic fluid for all those 10, having medium rich gas condensate or rich gas condensate, having high CO2 content, different liquid dropouts, different saturation dew point pressure. So it's giving a 10 different types of reservoir fluids, and we're able to match. Yeah, there have been many times questioned that, okay, whether synthetic fluid we are able to design synthetic fluid for different reservoir fluids or not. But we have never seen any reservoir fluid where we are not able to design a synthetic fluid.
And you have always used these 4 components?
Not 4, it can be any. Okay. We do the regression. Okay. So generally we have seen that we have C1 always, and diphenylmethane. That's I will say in 50% of the cases. But all this this intermediate hydrocarbon that will differ.
Yeah.
So that we find based on this regression, which combination will give us which component and which amount of different components. We do the regression to match this reservoir fluid data. I don't think we don't need to go into synthetic fluid paper.
No.
Okay, so a steady state procedure. I think here Curtis has already gone. So what we try with steady state relay are performed using different mixtures, which represents different mixtures coming from region 2 to region 1. So generally we try to have 5-6 different reservoir fluids, and then we take one particular mixture and we try to flow at different flow rates, at different rates to get this. If we are changing the rates, if we are higher rate, then we get this higher capillary number, and then we get different permeability. So which relative permeability, which indicates the effect of the capillary number. And then these experiments in the lab generally we do at a constant core condition, constant core pressure, which is close to the expected minimum well bottom hole flowing pressure. This the flow is the reservoir fluid is flowing till we get this constant delta P, and then constant delta P is used to calculate this permeability for the region 1. And this is showing one design the way we do. Let us say for this particular, in this particular case, we have taken this 6 different fluid mixtures. One is having dew point pressure of 5,500, second is 3,700, 3,200, 27, 22, and 1750. So what we take one particular, let us say 55 dew point pressure mixture, and then we are flowing at different pump rates. So this has the, and as we have a different rate, then we get this different delta P. We try to go, just we have to find what should be our rate. It should be 40 or higher or lower. So before going for this rate, we have to go in the reservoir simulation model, and we see that what is the expected capillary number based on the simulation model.
Near
the
close to the well.
Near the wellbore, what is the expected capillary number in the field, and we try to reach or cover that capillary number in the live experiment also. And this one, we are, for this example, this one is the for a core pressure of 1000 psi, and the same experiment is conducted at different core pressure, 2 different core pressure. This is at 2000 psi. So this is the pressure, and this 1000 or 2000, that will depend. Generally, we take from the full field models. What is the expected range of the bottom hole
in region 1?
In region 1.
Yeah. Near the wellbore, but even outwards. So.
There is a question.
Just says confinement pressure.
Yeah, so confinement pressure, while doing the live experiment, we have to use the same confinement pressure is, I think, same as net net overburden pressure. So we try to have the same confinement pressure as in the field. So before doing the experiment, we ask for the client what is the net stress or net confinement pressure in the field, and that we use here. And we try to keep constant. So maybe it's 300 bar or 200 bar. It depends whatever is in the real reservoir.
So this is this a different eclipse model, like a 1D?
No, this is nothing to do with the, this is only the calculation.
Arsenal.
Yeah, this is the Excel calculation.
Okay. Good.
So we are, yeah. So this is the design based on the whatever correlation we have. And this is showing that, okay, if we take a particular mixture, this one is, let us say, black one 5,500 psi mixture. This is a black line. We are flowing the same mixture, but at different rate. So in one, we are flowing at lower rate, for example, and then at 10 cc per minute, and we keep flowing till we get this stable delta P. Then we increase the rate to increase the capillary number to know the effect of the capillary number on the relative permeability. And then again, we go at the higher rate. So the increase for a given mixture, the increase in the relative permeability from 0.1 to 0.2, this is due to the effect of capillary number. If there is no capillary number effect, then we should have expected this black line to be horizontal. And as the fluid system becomes leaner, so even like without this at the very low rate, this is showing a type of rock curve or immiscible curve. So here is showing that for the richer system, richer fluid, this KRG is lower, and as we have seen in the previous calculation also, KRG becomes higher if we go from richer to leaner. So this one is showing for the leaner fluid, which has the dew point pressure of 1750 psi.
What does it say in the title? Effective KRG with beta versus pump rate?
Yeah, so what in the title is showing the beta, because this is the design. So this we do the design, and then this one we give to the lab. This is the expected. So with beta means while doing the design, because if you are doing the lab experiment, so in the lab we will have the impact of both non-Darcy and capillary number.
Okay.
And in this particular, when we see the beta, we are taking beta from correlation.
Okay.
But once you have got the lab measure data, it may not look the whatever we are designing here. It will look different. And then we have to find the beta for that particular code.
Do you have the same plot against the capillary number or against velocity?
No, I don't think here. I don't have
in
that.
In the spreadsheet you have it.
Yeah, in the spreadsheet we have. I think that's a good idea. I should have here also. But we'll also say the same. Yeah, it's not the similar, but whatever Curtis has shown previously with the capillary number trend we will get. But here we see that, for example, for the black line for the richer fluid, we see the impact of the condensate blockage in the design. Effect of the capillary number.
And on the right, you actually see the beta turning it around.
Yeah, so here in the right, where we have flowing at the higher rate, we see that the increase is due to the capillary number, and as we see there is slight decrease in the KRG, and that's due to beta.
And this beta, so this all calculation is done in Excel, and there you get the beta value. You just assume a beta value.
Beta, we take the default in the design.
Okay.
Because while doing the design, we don't know what is the actual beta. So beta in the design, we take from the correlation. And why we need to do the design? Because from the full field simulation model, we know that what is the expected capillary number near the wellbore. So we want to cover that capillary number in the live experiment also.
Okay.
Here in this case, we see large impact of the capillary number. It's going from 0.8 to
0.08.
Yeah. So it's 3 times. And the main reason is that here at 2000 psi, we'll expect lower IFT. And if you have the lower IFT, then we have higher capillary number.
Also the higher rates.
And higher
velocity
also we have.
So for dew points 3724, it goes on to plateau, whereas for 2750, it starts to decline. I mean the KRG. What is the reason for that?
Yeah, if you turned off the beta, if you had 0 beta, then those would be monotonically increasing always. The beta starts kicking in, at the highest velocities. So you get some improvement, and then you take away some of the improvement due to the beta.
Yeah.
Okay, and the velocity will be higher for 27.
Well, it's complicated, but I mean it's flat. It's almost flat for the richest fluid, and it's for the leanest fluid. It's actually turning around. We see it turn around sometimes in the lab.
Yeah,
in the lab as well.
Yeah.
So, but these are all just predictions, kind of like with default correlations.
Default correlation, default parameters. So this is the actual. This is showing one actual measure data. So this experiment was conducted on a 20 millidarcy core and at 1700 psi. And this is the live measure data. So if you see, it's increasing with increasing pump rate. And this is due to the capillary number effect. So this steady state experiment for region 1 is done for 5-6 different fluid mixtures to cover the range which we expect in region 1 and also at different rates. And these all measure data will help us to find the value of non-Darcy beta and capillary number model parameters.
And the immiscible curve as well.
And immiscible curve.
Complete.
So, and in the live experiment, we also suggest generally, if here we are saying saturation measurement are requested, then we can have one oil saturation measurement just to log this relative permeability with saturation. Then Curtis went through we like to have one measurements for the region 2 gas permeability just to see whether our region 2 curve is like S-shape or core type. Like if there is slightly increasing slight saturation in the oil saturation, then how the relative permeability of the gas will drop.
And that's only important for rich gas condensate.
That is important for the rich gas condensate. So what we do this, we take the at low oil saturation, we do one gas permeability measurement. And we have already gone through that, how we design, we take this CVD dropout. So we have to see the CVD dropout curve, and then what should be the liquid in the core at that time, and then do the experiment. Single phase. And then also we do this single phase gas permeability measurement. And here we just try to find the effect of the like non-Darcy parameter beta. And this single phase permeability measurement generally we do with different fluids, like the reservoir fluid, which is a synthetic fluid, then also with the methane gas, and also we just try to estimate from the region 2 gas. So what we do here in region 2 also, if we are doing the measurement, we try to do measurement with different flow rate. So with different flow rates, we can find the gas permeability, whether it is varying with flow rate or not. Because we have only gas flowing, so there is no impact of effect of the capillary number. If there is change in the permeability, that will be due to effect of the non-Darcy beta. And here we do this on beta. So with the region 2 gas, when we are doing multi-rate test, so we get this gas relative permeability in presence of oil, with oil less than the critical oil, plus we are also estimating beta from that experiment. So what we do, so we just try to have a different rate, and if we plot this du by dp by u and u, and then intercept will give us the permeability, and the slope gives us the beta. So if we have only the single phase in the core, single phase gas, then we get single phase beta. And while doing the experiment for region 2, where we have some saturation of oil, we get two phase or multi-phase beta. And what we have seen that there each slight different, you can expect different beta if you are using only the single phase gas, or if there is two phase. And even if you have the two phase beta, so, and those in Eclipse 100, there are different models to model this single phase beta or the two phase beta. So what we mean to say that if you have only water saturation, then we may get different beta. And if you have oil plus immobile oil, then we will get different beta. Yeah, so here we are saying that, okay, we have to cover this capillary number in the lab, which we estimate from the fulfill model. And then we decide the range of the pump rate or velocity. And here this is showing that, okay, what will be the, how much capillary number we want to cover based on the fulfill model. And then we do this calculation. And then we have to see that, okay, we have to find what will the maximum pump rate we want. We can go at a very high pump rate to cover this very high capillary number, but is that we have some limitation on the delta P across the core. And that delta P limitations comes due to this water saturation, while you are establishing this SWI based on the porous plate method. So here what is showing that capillary number cover for at this 100 psi core pressure is up to 1000 psi is up to 2 into 10 to the 5 minus 5. But if at 2000 psi we are doing the experiment, then we are able to cover capillary number up to 1 into 10 to the power minus 4. Yeah, so once all the live experiments have been conducted, then we have to do the analysis of the data, interpretation of the data, and then we have to develop this relative permeability model, including we have to find this KRG, including this KRG Chiaro, capillary number effect, and the beta. I don't think.
How far are you on?
Yeah, I think this is done now.
Okay.
Yeah. So this is done, and then once we have done the live experiments, we have done this capillary model development. So we have got this rock curve. We have got all the parameters from the for the capillary number model, and we got the beta. So that we need to include in the full field model.